Welcome back. Today, we're diving straight into the exact science of industrial emissions monitoring. We're going to unpack a really crucial regulatory document, EPA Method 17. If you've ever dealt with stack testing, you know how dense this stuff can be. So we are going to demystify the entire in-stack particulate measurement process and turn all that complex regulatory text into clear, actionable knowledge.
So, here is our roadmap for this explainer. We're going to break this down into 6 parts. The particulate matter problem, introducing EPA Method 17, the sampling train equipment, the 5% rule, sample recovery steps, and finally, why data quality matters. Let's get right into it.
Section 1, the particulate matter problem, defining the elusive pollutant. Okay, so measuring particulate pollution isn't as simple as, say, just weighing a solid object. Particulate matter, or PM, actually isn't an absolute quantity. It's a function of temperature and, well, to a slightly lesser extent, pressure. Temperature literally dictates how much PM is actually present in an effluent gas stream. Basically, if you don't define the exact temperature at which you're measuring, your measurement is pretty much meaningless. Now, to prevent that kind of variability, the EPA Standard Method 5 sets a nominal reference temperature of 120 degrees Celsius. But to maintain that exact temperature while pulling gas out of a stack, Method 5 requires this cumbersome heated glass sample probe in a heated filter holder. And let's be real, dragging highly sensitive heated glass equipment hundreds of feet up the side of an industrial smokestack is incredibly frustrating. But what if we know that for certain industries, the PM concentrations are totally independent of temperature? Why go through the hassle of heating it at all? Well, that exact question leads us to a much more elegant alternative. Section 2, introducing EPA Method 17, the elegant in-stack solution. Enter Method 17. This method completely eliminates those bulky heating systems by sampling the particulate matter directly at the actual stack temperature. It's brilliant. But, and this is a massive but, compliance officers can only use this method under very specific ideal conditions. The PM concentrations literally must be known to be independent of temperature over the normal operating range for that specific source. Plus, you absolutely cannot use Method 17 if the stock contains liquid droplets or if it's saturated with water vapor. The whole point here is capturing dry particulate right at its natural temperature without introducing any artificial heat. Now, we are about to literally look inside the smokestack to see exactly how this hardware operates. But before we get into the heavy schematics, if you love unpacking the exact science and engineering behind these kinds of regulations, take a second to hit subscribe. It really helps us keep bringing you these deep dive explainers. All right, Section 3, the sampling train equipment, visualizing the mechanics. Let's take a look at the complete particulate matter sampling train from the EPA documentation. Notice the layout here. Over on the left, you've got the components that are physically inserted right through the stack wall. Gas enters the sampling nozzle, immediately passes through that in-stack filter holder, and then travels all the way down the flexible tubing. Next, it hits the condenser section. Those are the glass impingers sitting in an ice water bath, and that's where the moisture gets stripped out. Finally, the dry gas flows through a dry gas meter and exits via the vacuum pump on the bottom right. It's this perfectly closed, highly regulated loop. So let's break down those vital components really quick. First up, the probe nozzle. This is designed for isokinetic withdrawal. That's just a fancy way of saying the gas enters the nozzle at the exact same velocity it's already traveling in the stack, which guarantees your sample is actually representative. Second, we have the star of Method 17, the in-stack filter holder. Because it's exposed to extreme stock conditions, it has to be made of incredibly tough materials. Think borosilicate, quartz glass, or stainless steel. And it uses silicone rubber or Teflon gaskets to make sure nothing leaks. Third is the Type S pitot tube to measure gas velocity, which has to be spaced perfectly from the nozzle to avoid any flow interference. And last but not least, the condenser or impinger system, which cools the gas and removes all that moisture so the final volume can be accurately measured. Section 4. The 5% rule, minding the blockage. Now, whenever you insert testing equipment directly into an exhaust stream, you're obviously introducing a physical obstacle. Imagine looking down the stack from above. You've got the stack wall forming the outer circle, and then there's this bulky in-stack filter holder pushing right into the middle of the flow. As the gas rushes up, your equipment is basically acting like a roadblock. So testers are actually required to calculate this cross-section blockage by taking the shaded area of the equipment and dividing it by the total area of the duct. And here is the magic number you absolutely cannot exceed, 5%. If your probe extension and filter assembly blocks more than 5% of the duct's total cross-sectional area, Method 17 becomes completely invalid. No exceptions. Why? Because that much blockage alters the flow dynamics so severely that your isokinetic sampling data becomes completely untrustworthy. If you hit that 5% limit, you have to abandon the method. You'd have to switch to an out-of-stack filtration method or physically separate your sampling and velocity measurement sites. It's an incredibly strict physical limitation. Moving on to Section 5, Sample Recovery Steps. Careful cleanup procedure. Okay, the test is done, the pump is off, and you've pulled the equipment out of the smokestack. Now begins the surgical sequence required by the EPA. First, you have to let the assembly safely cool. Second, wipe off any external particulate and cap the probe. But here is a really crucial little detail. You have to cap it loosely. If you cap it tightly while it's still cooling, the contracting air creates a vacuum that will forcefully suck the condenser water backward and literally ruin your entire sample. It's a crazy bit of applied physics that catches a lot of people off guard. Anyway, after it cools, you carefully disconnect the components, cap every single inlet, and immediately transfer everything to a clean, wind-protected area for an acetone wash. And finally, Section 6, Why Data Quality Matters, the bigger picture. We've spent a lot of time talking about silicone gaskets, cross-sectional blockages, and vacuum pressures, but what's the actual bigger picture here? Well, the EPA document states it perfectly. Adherence to the requirements of this method will enhance the quality of the data obtained from air pollutant sampling methods. Strict adherence to every single one of these meticulous details is the absolute foundation of reliable environmental protection. We can only manage what we can accurately measure. Which leaves us with this final, thought-provoking question. How precise must our scientific methods be to guarantee the air we breathe actually stays clean? The sheer level of meticulous engineering inside EPA Method 17 proves that true environmental compliance isn't just about broad strokes. It's a game of rigorous millimeters and incredibly strict percentages. I really hope this explainer gave you a clear, structured understanding of how in-stack particulate measurement actually works in the real world. Thanks for hanging out and focusing in with us today. And keep learning.